right, we are now recording. Let's start from current slide. I'll even turn on the projection for us. Okay, where is my class? 3 out of what, 18 or something like that? Ah, here we go. Brittany, right? Okay. All right. What do we have? 17. 4 out of 17, not quite a quarter of the class here. Before we get started today, let me go through a couple of, these are fairly, I think, probably minor announcements, but just to save you, in case you were going to be looking for me to save you the effort, let me go over this. Normally on Fridays, I'm on the Birmingham campus, 7:45 to 11:45, and supposedly they should be mostly office hours, which most of the time they are. However, they love calling meetings on Friday, but as far as I know, I don't have any meetings tomorrow, but that doesn't matter because I'm not going to be on campus tomorrow, okay? And the reason is I've got an infusion tomorrow. I've got to be at the Kirkland Clinic probably sometime around 7-ish or so. My infusion is scheduled to start at 8. Usually it goes close to 8 hours, so I will be out of pocket all day long. Will not be on campus at all. So don't go to the Birmingham campus looking for me tomorrow. I won't be there. I won't be on this campus either. I'll be at Kirkland. All right, so that's tomorrow. Monday should be much closer to normal. And by the way, remember what normal is on Mondays and Wednesdays now. When the math team wants to have a practice, I practice with them from 3:15 until 4:45 if they want to do it. So far, that's been few and far between, but I've been available if they needed it. So if they do want to practice Monday, we will be practicing. So that means we'll probably stop before 4:45 because that's when one of the students' class begins. So the odds are that I'll either have office hours 3:15 to 5:15 or 3:45 or so till 5:15. Okay, that's Monday. I can't stay much later on Monday. Most Mondays and Wednesdays I can stay a little later if I need to. I've got a meeting Monday off campus, so I'll be leaving shortly after 5:15. Tuesday, normally my only office hours on Tuesday and Thursday are 12:15 to 1:15. That's also my lunch hour, but it's the only time I'm in the office on Tuesday and Thursday to speak of any length of time. However, this coming Tuesday, I will not be because I've taken my physical science class on a field trip, and that means as soon as I get through with my 12:15 class, linear algebra, as soon as it's through at 12:15, I've got to book it to the Birmingham campus, pick up the van, book it back here as fast as I can so we can leave at 1:15 to go to the field trip. So Tuesday, don't look for me between 12:15 and 1:15. I will be on the road, getting the van and getting back on the road. Okay. After that, things get a little more normal, whatever that is. But then the following week is when second mini-term begins, I think, sometime in there. And then my office hours change on Tuesday and Thursday. I'll talk about that when it gets closer. Okay. Any questions on anything we've done up till now? All right, this is where we left off last time on this slide. We had just done example 5, and I told you about the checkpoint. The final type of transformation is the vertical translation. Hey, there's Ilsa. All right. Vertical translation. And remember, way back at the beginning, they introduced this concept, and then I said at the time I thought it was bizarre, but they still do it. We dealt with A, either sine theta or cosine theta, okay? A dealt with what? What did A influence? The amplitude. And then we introduced B, which dealt with the period. C was phase shift, left or right. And D, they put it in the front. Seems like to me they should put plus D. But I guess they're afraid you'll think it's part of the sine function. It's not. So they put it in front. this is the vertical shift. Okay, just like it was back in other functions that we did earlier. Okay, now the one thing I don't like about this I expressed before, I like to factor out the B, and then what's left in here, that's actually the phase shift. What you do now, you see refers to the phase shift, but it's not actually the phase shift. If you factored out the B, that would be the phase shift. So, but D is just strictly the units. If D is positive, you're shifting up D units. If D is negative, you're shifting down D units. All right. Remind me. Huh? Jeremy, that's what I thought it was. I had my finger on it. I wanted to make sure I didn't put mark the wrong person here. All right, so that's what D is a vertical phase shift. In other words, the graph oscillates. Now think of this. Sine and cosine functions are periodic functions oscillating between two values. Okay? Without the D here, the equilibrium position is the x-axis, right? With the D in there, now you're shifted up or down, and that's your equilibrium position is shifted up or down that far. So that combines with the amplitude, so you're going from A plus B down to, or let's say D plus A down to D minus A. And that's where you go from there. Any value you would have is shifting. So your amplitude, everything goes up and down with the D. Okay? So, they tell you about it, but then they don't show you an example. So let's go back and do an example. This looks like a good place to do the example. This will be example 6. Sketch the graph of y is equal to 2 plus 3 cosine 2x. Okay? Now, I want you to identify for me your parameters. What do you notice about this? In other words, tell me what A, B, C, and D are. A is 3, okay? What does that influence? What is the amplitude then? It's also 3 because it's absolute value of A. All right? Next. B is 2. It's that 2, not the first 2. What does that influence? Period. And how does it influence the period? How? Yeah. What's that? Yeah, it does stretch or shrink. Is that what you're thinking of? I saw your hands doing that. I thought you were playing the accordion, but okay. But what's the formula for period then? If we know B, how does that help us find the period? 2 pi over B, and B here is 2. So what I say 2 pi and write 2B. There's something wrong with my brain, you know, or my hands, or my something, okay? It's 2 pi over B, and B is 2 pi over 2, and so in this case the period is pi. Okay. What's that? Okay, and then the next thing that you're reading my sick mind. Okay, remind me. Taiwan. No, you're in here. There you are, Taiwan. There you are. Just below the. There you are. All right. Okay, once I find the period, then the next thing I do is divide the period by 4. So our intervals then will be pi fourths. So it's related to the period, divide the period by 4. Determine what the period is, then divide it by 4, and that gives you your interval. Okay? How about C? There is no C. C is 0. There is no phase shift. So forget about that one. And then finally, D is 2. That's a vertical shift up or down. Okay? Now, let's do the graph. And it's a cosine function. Now, do you think you would find it helpful ooh, that's pretty ugly. Get out of there. Okay. Okay. Do you think you would find it helpful to graph the parent function cosine first and then do all the things to it, or can we just proceed from here? Proceed from here? Okay. All right. Normally, I ask myself, where does cosine, well, wait. Let's get our scales in. Okay? 1, 2, 3, 4, 5, 6, -1, -2, -3. I'm not going to need all that, but I'm going to put them there. The intervals on the x-axis, though, that's where I use the pi fourths. So this will be pi fourths, pi halves, pi, and somewhere out there is 2 pi. Okay? This will be minus pi fourths, minus pi halves, and somewhere out here is minus pi. Now I can't get minus 2. Quit! Why is it doing that? Okay. Minus pi. Okay? Now, normally I say, where does cosine begin? So let's say it. Where does it begin? Normally, just cosine function. 1, right? Starts at 1. And since we don't have a phase shift, it'll be okay. So normally it would start at 1. But then I'll look at the amplitude and see that's 3 times. Oh, here they come. All right. Justin came in. And the Jorian's still missing. Got it, thank you. And Mike. Okay. Yes, sir. All right, good deal. Anyone else come in since I called roll? Okay. Oh, here they come now. Open the floodgate. I can't remember. Have you already chosen a paper topic? You have? What is it? Can you remind me? If you don't remember, that's fine. The reason I asked, did you ever go to Bryn Mawr, or you just have the shirt? I don't know how to pronounce it. All right, you just have the shirt. The reason I asked that, one of my favorite mathematicians that people have written on before was a lady called Emmy Noether. She was a brilliant mathematician, but she lived back at a time when women weren't allowed to go to college. So I think her dad was a mathematician, so he taught her for a while, but she was surpassing him. And finally, they let her sit in on classes at the university where he taught, but wouldn't give her a degree. She blew everybody out of the water, but they wouldn't give her a degree. I can't remember if she was fully Jewish or part Jewish, but anyway, she had Jewish blood, and it was back at the time of Nazism in Germany. She was from Germany, and so she had to immigrate to the U.S. But I think still while she was in Germany, she sort of palled up with this other scientist. What was his name? Albert Einstein, I believe it was. Yeah, that's the one. Okay. And when he needed help in math, he went to Emmy Noether. I mean, she was, huh? Yeah, and she helped him through some of his algebra, really complex algebra, okay, and doing some of the theories he did. And she ultimately came to the U.S., and he did too, to get out of Nazi Germany. And she was at Bryn Mawr. How do you pronounce that? I don't even know.
My sister went to Bryn Mawr.
Huh? Your sister?
Mm-hmm.
Okay.
But yeah, it's Bryn Mawr.
Bryn Mawr? Mark. Okay. Okay. And she actually was on faculty there. And they may have given her finally her honorary degrees. And then the so sad news is she had a fairly minor surgery and died on the operating table. So I think may actually be buried on campus. I'm not sure, but fascinating woman. Let's see. I got off onto that.
Did you want me to talk about that?
What's that?
I said, did you want me to talk about that?
No. I just, when I saw you straight, every time I've seen it, I think, Emmy Norther. Okay, so I just had to say it today. I didn't have to, I chose to. Let me get your name to Darius? No. Jawan. Okay. I just was looking at your name. I can't see it. There it is. All right, anyone else come in since I called the roll? Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10. 3. Yes. Broke double digits. Very good. Okay. So, where were we? We said normally cosine starts at 1, but we have an amplitude of 3, so this one would be starting at 3. Okay, they keep coming. All right. Terrell is here. And Taylor? Is that right? Okay. All right. Any others come in since I called roll? All right, we're trying to graph this function, okay? Where we began, I like to begin at the beginning. That's a good place to start, right? When x equals 0, normally cosine is 1. But the amplitude jacks it up to 3, okay? But the vertical shift jacks it up to 5. So we're going to start at 5, okay? Now, the vertical shift jacks everything up by 2. So whereas normally our equilibrium line would be at the x-axis, now the equilibrium line is x equal 2. And you don't have to do this. I like to dot that in to let me know everything's going to go up and down around that. Okay? So I'm going to use that as my basis. Okay? Now, we've already dealt with the period is the parameter 2. B is equal to 2. Period is 2 pi over b, which is 2 pi over 2, which is pi. That makes the interval. Divide that by 4, the period by 4, and that gives you interval pi fourths. So from the maximum, it goes down to equilibrium. It used to say go down to 0. Now it goes down to equilibrium. And then it goes, the next quarter cycle, it goes down to the minimum. And the minimum would have been a -3, but that gets jacked up by 2, so it's -1. So it goes back to 0, back to 5, back down to equilibrium. I said 0, didn't I? It's equilibrium, and back down to minimum, which is -1. I went too low on that, I think. And then back to your equilibrium again, okay? And going in the opposite direction, it goes down to equilibrium. The next one goes down to the minimum, -1, back up to equilibrium, back up to 5, your maximum, back down to equilibrium, and back down to your minimum, which is -1, and ultimately we go back here. All right, so this is what, if I can find the point. Pretty ugly drawing, but there it is. All right. Okay. What has occurred here? The amplitude has been raised from 1 to 3. The B has horizontal squeeze. Okay. It would have been a period of 2 pi. Now it's a period of pi. So you see one period is now pi. So there's your horizontal squeeze and your vertical shift. Everything went up. The equilibrium went up 2, the max went up 2, the min went up 2. So everything goes up 2. Does that make sense? Okay? Now, You see in the text, theirs is not quite as pretty as mine, but close. Okay. So, any questions on that? All right. Now comes an opportunity to try to put things together the other way. Okay? We've been given a function. Let's graph it. Now what we're going to do is called it's called mathematical modeling, but what we're going to do is start with data, try to map the data, and then come up with a function that fits the map. Okay? This is all we got, folks. The table shows the depth in feet of the water at the end of a dock at varying times during the morning. Okay? So the time t equals 0, that would be midnight. Then 2 a.m., 4 a.m., 6 a.m., 8 a.m., 10 a.m., and noon. So that's all we've got. From midnight till noon, we've got the depth of the water from those times. Okay? Now, so far they haven't asked for anything. Let's just take a few notes of it. What appears to be happening? At midnight, we're starting at depth of y. By 2, it's getting deeper. By 4, it's even deeper. By 6, it's coming up again. By 8, coming up. By 10, reaches a minimum, and then starts getting deeper again. Okay? This is the depth of water at the end of a dock. Okay? Now, so what appears to be happening here? You have, and if you know anything about it, you have the tides. That's what makes the water move up and down. The tides are not quite a monthly occurrence, well, not monthly, daily occurrence. They go through the cycle basically twice a day. Okay? As the Earth spins, the sun's in one position, the moon's in another position. Those relative positions of the sun and moon to the Earth, whether it's attracting or whatever, that is what creates the tides. And it happens high tide about twice a day, low tide about twice a day. So what we see is one high tide or something close to it, one low tide, and this seems to be back up, and it was going up here, maxed out, going down, in, and going back up again. Ooh, okay. Somebody else knocking on me. Okay. Kanisha, right? Chelsea, sorry. Okay. Has anyone else come in? Okay, I think I got everybody else. Okay. Okay. So that's the pattern. Let's see what they're asking us. Use a trigonometric function to model the data. So that's why they call it mathematical modeling. So let's use a trigonometric function to model the data. Now, what they do first is plot this, and that's not a bad idea, okay? But I think we can deal with it without actually drawing the graph. What were some things that I picked out that you related to? What's the easiest thing to pick out of that data? Say again? The tides rise and fall. Okay, the rise and fall. There's a maximum, there's a minimum. Okay. Now, they say model the data using a trig function. Okay? And if you were to graph this, this starts at 3.4, goes up, comes down, down, goes up again. Okay? Well, it looks like to me this is starting from near 0, not from the minimum, but close to it, right? Not from the minimum. There. So we get to choose whether a sine or a cosine function, right? Now, which you think looks like this would fit better, sine or cosine? Cosine. Okay? It's fine to use cosine. The book does. But to me, since it's going up, a sine function goes up to begin with. A cosine cosine function comes down to begin with. So I'm more inclined to use sine. But the book, I think, uses cosine. So either one will work. It doesn't really matter. Because I'm the boss. No, okay. We're going to do y is equal to, and let's put all of them in here. A is the amplitude, or has to do with the amplitude. Sine of, and I like to do mine like this, B times t, the independent variable is t minus c. Now, this isn't the way the book does, this is the way I do it, plus d, okay? So y is the dependent variable, depth, and time is the independent variable, because these are hours, okay? Now, someone remind me what amplitude is. Just in general, what it, yeah, okay, I saw this. What do you mean by that, okay? Okay, not wavelength, that's this way. It has to do with maximum min. How does it have to do with maximum and min? Is it the difference between maximum and min?
Yes.
Not quite. It's the difference between the equilibrium and the max, or the equilibrium and the min. So the amplitude is twice the value, the difference between max and min, because you have a plus amp and a down amp. You have two of those in there. So the amplitude is half the difference between the maximum and the min. So there we've got our A right there, don't we? Okay. Your A is 1/2 the difference between the max and the min. Do you buy that? Does that make sense? Okay. So what's your max? 11.3 minus the min 0.1. That would be 11.2. Half of that is 5.6. Okay. And that's going to be a depth, and they didn't give you measurements here, did they? Oh, in feet. So that's 5.6 feet. Okay, pretty decent size tide here they have. So we got our A, 5.6 feet. Bang, got it. Okay. Now, what you want to go for next? We still got a B, a C, and a D. You choose. B, okay? What does B relate to? The period. Now, how can we relate anything to period here? And again, it probably wouldn't have been a bad idea to draw this, but again, the easy things to pick out are your max and your min. So if you have a max here and a min there, how is that related to a period? Maximum to minimum. You went back up to the max, you would have gone one period, right? So max and min would be half of a period, right? So the period is measured in what? Is that the y's or is that the x? That's the x. That's the independent variable. So what's the difference between the times of the max and min? Again? 6. And that would be half a period, right? Did we just say that? Time to at max and min, that would be half a period, because back to max would be a full period, right? So the difference in times, the x, the t values here, that's from 4 to 6, that would be, 4 to 10, that's 6 hours, that's half of a period. So the period would be, again, 2 times 6 is 12. And didn't we just say you had high tides twice a day, low tides twice a day, most days? Yeah, that makes sense. So your period We don't know B yet, but your period is equal to 12 hours. Okay, we don't have to have the unit there. Say again? Okay, we'll do that. If we were going to plot, we would. But the period is 12 hours. Okay? Now, what we're trying to get is our B. How is B related to period? Or period related to B? Second. So period, which is 12, is equal to 2 pi over B. So let's figure out what B is. Anyone got it? Second? Okay, I couldn't hear you. I don't think so. Let's multiply both sides by B. Okay, that wipes out the B in the denominator, and then divide both sides by 12. Okay, so B is equal to pi 6, isn't it? Okay, so B is pi 6. We have A is equal to is 5.6, and B is equal to pi 6. We're not going to give it a unit. Okay, now, all right. Now, I chose to do sine. Sine usually starts at the equilibrium point. Okay? So your C is where the equilibrium point is relative to where we're starting. Okay? Well, where is the equilibrium point? And again, here's just something to note. A reflex is associated with the Y's here, right? D is associated with Y. The B and the C are associated with T, right? B is multiplied by T, and C is subtracted from T, right? So those are dealing with this. So we're dealing with the T values here for C, okay? What we need to find is the equilibrium position, okay? Is it Darius? Yep. Yeah. I'm finding you. There you are. All right, good deal. So we're only missing the Jarian. How did I do this? Huh. Okay. I went up a space. So Brittany is here. I went. Yeah, I really messed up. Okay, I've got to clear something up here. Dejarian was not here on. Okay. Sorry, I messed up my roll here. I went across this thing in the middle, and I went up a notch. Okay. Brittany, you were here Tuesday and today, right? And Justin, you were here Tuesday and today, right? Okay. All right. The Jarian was absent Tuesday and so far hasn't come in today. Whitney, were you here both? Okay. That's where I messed up. I took care of it. I got online after that. It's just the top three I had messed up. So, all right. So we're just missing the Jarian, Doc, and Kenesha, right? All right, now let's get back to, we've determined A, 5.6. How did we get there? A is half the distance between the max and the min. And these are Y values, so half the distance between 11.3 and 0.1 is 11.2. Half of that is 5.6. Okay, that's your A. Okay, your B was related to the x, that was twice what you have. Right, okay. The period is twice the time between the max and the min. The time between max and min is 10. Twice that is 12. That would get you back to max again. That would be one period. So if the period is 12 hours, then period is 2 pi over b. That gives you b to be pi 6. So your b is pi 6. You got that. C is the phase shift. Okay? Now here you sort of have to do some mental imaging here. Okay? Let's think in terms of sine. Okay? Here you have a maximum of 11.3 going down to a minimum of 0.1. Okay? Now, half the distance time between these two is when you're at equilibrium, right? Between max and min, you're at equilibrium here. And then that same time on the other side of your max would be when you're at equilibrium again, because your sine starts at equilibrium, goes up to max, down to equilibrium, down to min. So halfway between the time between your max and your min is an equilibrium time, and then that same time before the max would be your first equilibrium time, right? So let's get the time midway between 4 and 10. What's that? Midway between 4 and 10.
6.
Second? You may have said it wrong.
7.
7, exactly 7. Okay? So 7 would be that one, and the difference between 7 and 4 would be, in fact, we're doing what you said, we're doing your quarter periods, right? Your period was pi 6, okay? Well, except, okay. Your period was 12. Period was 12. Half of that was 6. A quarter of that is 4. Right? Is 3. A quarter of that is 3. So 3 hours before your max would have been your starting time. And that would have been at 1 o'clock. So at 1 o'clock, that would be your C. So the C is 1 in this case. So C is equal to 1. Now they don't call it that, okay? They call it C over B is equal to 1. I like to call that my phase shift. Now finally the D. The D is how far we already determined A here, okay? Let's go back to our max and our min, okay? Okay. Here's max and min, okay? They're both above 0 because see, this is here. Your normal would be down here. You shift it up. You shift it up a certain amount from there. Now, how far is that? We already said your period was half the difference between those two. Your phase shift would be your average between these two would be your equilibrium position, and the equilibrium position would be how far above the x-axis. That would be your D. Does that make sense? So let's take the average between these two. Again, these are y values there. So this time we add the two of them together. What does that give you? $11.4. Take half of that. 5.7. There's your D. Okay? So your 5D is equal to 5.7. Okay? I think we have everything that we need. So let's write it down. Y is equal to A, 5.6. Now I'm not going to put the feet in there, but you can do it. It just makes it too long. Sine of your B was pi 6, okay, times t minus the phase shift 1 plus 5.7. There is your model of how to anticipate the tides, okay, at least on that day, okay, between midnight and noon. That would give you a good estimate. Y is equal to 5.6 sine of pi 6 times t minus 1 plus 5.7. Now, the book is going to multiply this by minus 1 and have that there too. That's what they call their C. I like to call the C the actual phase shift, to factor out the pi 6. Now, they don't call it pi 6 either. They call it 0.5 something another. If someone will take pi 6, divide pi by 6, see what you get. It's 0.5 something. Anyone got a calculator? Pi divided by 6. Pi is 3.1416 divided by 6. About 0.523 or something like that. All right, so let's see how we did. Y'all got it down, right? They graphed it first, and that may be helpful. If it is, graph first, you know, just sometimes it's sort of a pain in the neck, okay? And they said you can either use sine or cosine. They chose to do cosine, I chose to do sine, okay? Guess what? The A's going to be the same, the B's going to be the same, and the D's going to be the same. The only thing that's going to be different is C, okay? So here's what they did. A was 1/2 the difference between max and min. Yeah, we did that. Max and min, we did that and came up with exactly 5.6. Got it. It's in feet, by the way. Okay, the cosine function completes 1/2 of a cycle between the times of max and min. So the period is twice the time between your max and the min. We determined that to be 10 to 4. 2 times 10 minus 4 is 6. So your period was 12. Implies the B is 2 pi over period. Okay? And that gave us 0.524. Isn't that what you got when you did pi divided by 6? Okay. So they use 0.524. I use pi 6. Who cares? Whichever. Okay? Because the high tide occurs 4 hours after midnight, consider the left endpoint to be C over B equal 4. So C is about, divide that by your B, about 2.09 blah, blah, blah. Okay? That's because they're using the cosine function, and they're also doing C over B. What I called C was C over B. There's C over B. Subtract 4 from that, and subtract 3 from that, and you got 1. So I find mine's a little easier to use, but anyway, so far we're together. And moreover, because the average depth, not the difference, but the average depth is 1/2. The average depth is 1/2 of the high to low, and the average is going to be your equilibrium. That's where D is. That's how far above that you did. So there is their model. 5.6, they did cosine, I did sine. I did pi 6, they did 0.524, same thing. T, I put this on the outside and did T minus 1. They put it on the inside, and actually, if you multiply 0.5 by 2.9, someone do this. 0.524 times 2.94. 1.9 something? 0.97, that's what I thought. That's just a little bit more than 1. So you see, we're we're still on the same, writing the same thing. And then plus 5.7, okay? Now, let's go back to the B part. All right, the B part says find the depths at 9 a.m., okay? And then at 3 p.m., okay? So let's go back to our formula here. And our formula was, I need to write it somewhere else. So let me write it up here. Y is equal to 5.6 times the sine of pi 6 times t minus 1 plus 5.7. Okay? Now I'm going to erase all the rest of it. Okay, is that okay with you? All right. You got it down. You can find it if you need it. Okay? This is all the calculations they were making. Okay. Okay. Now, their question was, find the depth at 9 a.m. Well, 9 a.m. would be time t equal 9. So y would be equal to 5.6 times the sine of pi 6 times 9 minus 1 would be 8 plus 5.7. Right? Okay, pull out your handy dandy calculators and start plugging in numbers. Okay? 5.6 sine, and it's going to open a parentheses for you. Now, I'm just going to do a little bit of work on my own here. 2 will go into 6 3 times, 2 will go into 8 4 times. That'll just make it a little bit easier. Not much. 5.6 sine times sine of, it opens a parentheses here for you. I would say 4 times pi, you got a pi t, divided by 3, close the parentheses, and then add 5.7. See what you get. Anyone got a calculator and punching it in? A little louder? 28.1? Whoa. Way too big. Okay. Okay. Let's try it one more time. 5.6 times sine of an open parenthesis 4 times pi divided by 3. Oh, okay. What mode are you in? Radian or degree? It still shouldn't be. You're in radian, good, okay. 5.6 times sine of 4 times pi divided by 3, close parentheses, plus 5.7. It can't be 20 something, okay? Just no way. Anyone else punching it? In the South, we're violent. We punch numbers in. In the Midwest, they press the numbers. They don't touch them. Oh, goodness. Let's see. Tell me what you do. You do it. 5.6. Yeah. They gave us, well, 4, well, pi times 4 divided by 3. However you do that. Yeah, times 4 divided by 3, close parentheses, plus 5.7. Yeah, oh, 0.85. Is that what you said? Oh, okay. Okay. Okay, 0.85. That sounds a little low, but let's see. Oh, no, it doesn't. Look at this. 9 a.m. is something between 3 point. Okay, what did you get? Read it to me. 0.85. Is that what you said? Okay. 0.85 feet. Well, I'm going to just make a guess here. Let's take the, and this isn't linear, but if we did take a guess, like the average between that, 3.9, half of 3.9 would be 1 point. So that is in between these two. That feels good enough to me. 0.85 feet. Okay, now here's the next one. 3 p.m. 3 p.m. is even on our table. But how many hours after midnight is 3 p.m.? If you're in the military, you know that right off the top. You don't call it 1, 2, 3, you call it 13, 14, 15. So let's plug in 15 there. So let's do different color. Give me a color. Red. Okay. All right, we got red. Y is equal to 5.6 times the sine of, I'm going to write it 4/3 pi. Oh, no, I'm not. Sorry. Back up. It was pi 6. Got to go back to what it was before. Okay, pi 6 times t minus 1. We said t was 15, right? Minus 1 would be 14 plus 5.7. So try punching those in. Now, to make it a little easier, 2 into this would be 3, 2 into that would be 7. Sorry. And you know what? If I had been thinking about it, I could have figured what 4/3 sine of 4/3 pi. That's one of our favorite ones, isn't it? Here's 1/3, 2/3, 3/3, 4/3. That would have been down here. The sine of that angle would be square root of 3 over 3, wouldn't it? Okay, so that was 4/3. 6/3 would be here. This would be 1/3. 1/3 pi would be root. That was a minus root 3 over 3. This is positive. I mean root 3 over 2. Positive root 3 over 2. So whatever. Your calculator will take care of that. What do you get? Has anyone punched it in yet? You got a calculator? You punching? Okay. Huh? No, that's a little too large. Second? 10 point something sounds awfully good to me. Say that one more time. 10.225? 0.55. Let's just call it 10.6. Okay? 10.6. Well, guess what? 3 in the afternoon, since it's a period of 12, should be the same as 3 in the morning. And 3 in the morning, 10.6 looks pretty good to me. Okay? Did you get it? Should be something between 11 and 9. You still don't? Okay, let me watch you do it. Okay, yeah, clear that. Starting. Times. Okay, sine. Okay. Now you got an older calculator. Okay. That's the problem. We have to. I don't know how to turn this thing off. Okay. What you have to do is put the argument of sine first. Okay, so you have to start with 7/3 pi. Do you have a pi key on there? Yeah, you do. Okay, so 7 times pi. I didn't hit it, did I? No, that's an N. I can't read. Oh, I see. Let's start over. You start with the argument of pi, argument of sine, which would be 7 times, I guess that's the shift. Yeah, got it. Divided by 3. Okay. That's what that is. Then you do, and you're in radian mode, that's good. Then you do the sine of that. That is your square root of 3 over 3. Then multiply that by 5.6. And then add to that 5.7. Now, if you have an older, what I call the scientific calculator, most of the old scientific calculators, you have to put the argument first, then do the function. It's kind of like inverse notation or something. But if you have the newer, what I call display kind of calculator, you can just do it as you go. But yeah, on yours you have to do the argument first and then multiply and add and things like that to it. Yeah, about 10.6 feet. Okay, let's see what they got. We got 0.85 feet and about 10.6 feet. Let's see what they got. Goodness gracious. Here we go. 0.84, close enough for government work, and 10.57. Okay, very good. Now, part of their error comes from the fact they rounded off to 0.524. So I like ours better. Okay. Now, that wasn't all of it. What's the third part of this? A boat needs at least 10 feet of water to moor at the dock. At what times in the afternoon can it safely dock? Okay? Now let's go back to our formula. And here we have our formula. So what we need to do, our y, now let's do a different color. What color you want this one? Green? Okay. Dark green? Huh? Is that all right? Okay. Dark green. Now, that's what we need. You need y to be 10. So 10 is equal to 5.6 sine of pi 6 times t minus 1 plus 5.7. Okay? Run out of room again. Okay, we got to work backwards now. We got to find out at what time in the afternoon. Okay, so between what two times? So let's go back to, and what are we going to have to do? Now we have to subtract 5.7 from both sides. So this leaves 4.3 is equal to 5.6 times the sine of pi 6 times t minus 1. Okay? Next thing I would do, divide by 5.6. Okay? So some of you with a calculator, tell me what that gives you. 0.7. Let me get rid of this because whatever it is, I don't want it anymore. Okay, whatever you have on your screen, okay, is equal to sine of pi 6 times t minus 1. Now, I'm going to do something we haven't quite done yet, but hopefully you'll know what to do. Let's do an inverse sine. So that number you have on your screen, don't round it, that whole number there, 0.7, whatever it is. Do an inverse sine of that number. Okay. 0.8 something another, whatever you got on there. Okay, that is equal to the pi 6 times t minus 1. Because you did an inverse sine, that's what you got. Okay, multiply that by 6 and divide by pi. Whatever you had on the screen, just multiply by 6, divide by pi. 1.5 something another. That's equal to t minus 1. All right? So add 1 to both sides, and you get about 2.5. Okay? Right? So that would mean, and it said in the afternoon, that would be the earliest time that you get to 10. And that makes sense, about 2:30 or so, whatever it is. In the afternoon, you get to 10. And then you got to do, it said, between what two times? Well, there's some other time in the afternoon that you're going to be that, okay? Now, the other time that you would do that would be and here you have to go back to your sine function. Okay, it's like this, between this time and that time. Well, what's the relationship between that? That would be, okay, here was the, boy. Okay, what they did was do it graphically, and that is a little easier, which I'm sort of doing here. But you need to go as far. Remember, our max was at 4. So if this was at 2:30 in the afternoon, that's an hour and a half before the max, right? Then do an hour and a half past the max, okay? So that would be, I'm sorry. Yeah. An hour and a half past 4 o'clock would be 5:30. So anywhere between 2:30 approximately and 5:30. It's not going to be exact. So let's see what they get. Okay. Depth. Okay. They said using a graphing utility, graph the model with the line y is equal to 10. And you look it up, and they got 14.7. We were saying 2:30. They were saying a little past 2:30 to 5.3. So whatever that turns out being, that would be about 2:42 afternoon. I was rounding to 2:30 to about 5:18. I was rounding to 5:30. So you see, we're in the right ballpark. They did it using a graphing utility. We did it using the actual function. Okay. So if you don't have a graphing calculator, this would be hard to do. Doing the way we did, we'd get it to you otherwise. Doc came in, right? Okay. There you are. All right, we're just missing Dejarian and Kenesha. Is that right? Okay. All right, that is the last slide in the slide set. So let me back up one. Let's do our vocabulary fairly quickly. One period of a sine or cosine function is called one blank of the sine or cosine curve. One period of the cosine or sine or cosine function is called one blank of the sine or cosine curve. Say again? Did you have a word for it? One period of the sine or cosine function, which you, let's just pick a place from here to there. Okay? What would we call that of the curve? There's a couple words you can put there. One that I think of is cycle. One cycle of the curve. If you go back to the very first of the section, I think they call it, yeah, they call it one cycle. Yeah. One cycle of the sine curve. So one period of the sine function is represented by one cycle of the sine curve. Number two, the blank of a sine or cosine curve represents half the distance between the maximum or minimum values of the function. What's that? The blank of a sine or cosine curve represents half the distance between the max and min values of the function. We just did it in that last example. Amplitude, exactly. Number three, for the function y is equal to a sine bx minus c, c over b represents the blank blank of the graph of the function. Phase shift, exactly. Number four, for the function y is equal to d plus a cosine b x minus c, d represents a blank blank of the graph of the function. D is the vertical shift. Okay, exactly. So homework exercises here. Do any of the odds 5 to 17, any of the odds 19 to 29, any of the odds 31 to 37, any of the odds 39 to 59, any of the odds 61 to 65, 67 to 71, either 73 or 75, or both, either 73 or 75, 7 or 79, or both, do 81, and then do any of the odds, and this is more like what we just did, 83, either 83 or 85, or both. Okay? I'm sorry? This is 306 through 309. Yeah, 306 to 309. Okay, and after 83 or 85 or both, do any of the odds 87 to 93. They are more like the ones we just did. And then you're welcome to look at exploration. There's the one true false. There's some conjectures. Approximations, various things there. So I'll let you decide that. Okay? Any questions? Now, let's move on to 4.6. 4.6. This takes so long to load. I'm so sorry. Okay. We'll start from the current slide. We're still in trigonometry, but this time we're doing graphs of the other trigonometric functions. What two graphs have we talked about? Sine and cosine. So in this section we're going to do the other four, which are tangent, cotangent, secant, and cosecant. Okay? So what we'll first is sketch the graphs of tangent functions. It's going to be pretty straightforward. There's one little wrinkle that we haven't hit before. Once we got that, graphs of cotangent are pretty easy too. Then we'll do sketch the graphs of secant and cosecant. They turn out being almost the easiest ones to graph. Okay? Not quite, but close. And then we'll sketch the graphs of damped. Be sure you put the PD in it, okay? Trigonometric function, okay? So let's start with the graph of the tangent function. Now, what do we know about the tangent function already? No, tangent is sine over cosine. Sine is what kind of function, even or odd? No, sine is odd, cosine is even. And when you divide an odd by an even, you still have an odd, okay? So tangent is an odd function. They just sort of came out with that from nowhere, but indeed it's true, okay? Consequently, and here's the other way you can tell. Remember our quadrants? All students take calculus, okay? All the functions are positive here. Only the sine and its cosecant are positive here. Tangent and cosine are positive. Cotangent are positive here. Cosine and secant are positive there. Okay? Well, sine starts positive and stays positive. So, and over here it's negative. So therefore it has to be odd. Okay? Because it's what's here to here. Okay? Positive and negative. Okay? Tangent is also positive here and negative here, so it also is odd. Cosine, on the other hand, is positive here and positive there, so that indicates it's even. Okay. So, tangent is indeed odd. Consequently, the graph of the y is equal to tangent x is symmetric with respect to the origin. Okay? Now, you also know from the identity tangent is sine over cosine. Tangent is not defined anytime cosine is equal to 0. You can never divide by 0. And where is cosine equal to 0? Think of the cosine function. It starts at 1, it goes to 0 at pi halves, 3 halves pi, 5 halves pi, 7 halves pi, 9 halves pi. So all the half pi's, cosine is 0. So for those values, your tangent is not defined. So that's the plus or minus pi halves, plus or minus 3 halves pi, plus or minus 5 halves pi, plus or minus 7 halves pi. All your half pi's tangent are not defined. Okay? That's going to help us graph them. Okay? Because at half pi, negative half pi, undefined. At positive half pi, undefined. Guess what we can draw at an undefined value? Vertical asymptotes. Anytime you try to divide by 0, you get a vertical asymptote. Okay. Tangent is 0 at 0, undefined at pi halves, undefined at negative pi halves. Exactly in between that is pi quarters, right? Halfway in between, therefore tangent is equal to plus 1, and at negative pi quarters is at negative 1. You know that because it's the tangent of pi quarters is 1, and tangent of negative pi quarters is negative 1, because sine over cosine. They're the same at those places, except for the sign here. So there are our 4 points. Vertical asymptote here, 0, vertical asymptote, and halfway in between that, minus 1 and plus 1. And from there you can do it. As indicated on the table, tangent x increases without bound as you get closer and closer to that pi halves, and decreases without bound as you get closer and closer to negative pi halves. So therefore it's a vertical asymptote at minus 1, 0, plus 1, and positive infinity. Okay? So here's what it looks like. Okay? This will be the last slide. Okay? 0, plus 1, minus 1. So your couple of things. The period for tangent, unlike sine and cosine, is pi. And the reason for that, if you think about it, tangent is positive, negative, positive, negative. So it goes through one cycle in pi rather than going through one cycle in 2 pi. So its period is pi. Okay? And if its period is pi, you know that negative pi has its vertical asymptote, positive pi has vertical asymptote. So going to negative infinity, negative 1, 0, plus 1, positive infinity. And then repeats it, and repeats it, and repeats it, and repeats it over and over again. Domain is all real numbers except your half pi's. The range is minus infinity to positive infinity. Unlike sine and cosine, the range is plus or minus 1 in between those two. Vertical asymptote, everywhere it's not defined, vertical asymptote. And here's how we say that. Pi half plus n pi. Because period of pi, every period you run into another. And half pi everywhere after that. It's symmetric about the origin, meaning it's an odd function. Okay, we'll pick up next time then on this page. Moreover. Where is moreover? All right, have a good weekend. We'll see you on Tuesday. Got it, thank you. Yes. Okay, say again.
When are your office hours tomorrow?
Tomorrow, okay. I was saying that earlier. You must have come in after I said it. I'm normally on the Birmingham. It's out of state. Okay. I'm normally on the Birmingham campus on Fridays. However, I have an infusion tomorrow, so I'm not going to be on either campus at all tomorrow. So, what did you need?
I wanted to turn my report.
Okay, what you can do? Are you going to be on this campus tomorrow?
Well, I can come now.
Okay, if you can come, slide it under my door. And that way I'll pick it up Monday morning. My office is 265. You go down this half flight of stairs, and you go all the way, almost to the end of the hall. The last door on the left is the stairwell, and the door right before that, between the mechanical room and the stairwell, is my office. Right across from the orientation pattern.
So, a few of the problems, or maybe a couple of them, I didn't really understand the wording of them, so I didn't do them because I really didn't understand what you were asking.
I told you that's why I give you time.
Yeah, no, I was just saying.
Always ask.
Yeah, I didn't know that, but that's just something. Look my name on it.
What's that?
I said, look my name on it.
Oh, otherwise I'd just give it to anyone I want to. Huh? You don't have to do that. Okay. Okay.
Yeah, these two, or these three, were the ones that I had the most issue with.
Okay.
Yeah, it was just,
I actually answered this one in class, and if you listen to the YouTube video, you'll hear that one talked about.
Mm-hmm.
This one, you just have to figure out what the corresponding angle that is between 0 and 2 pi, and then do it from there. It's going to be one of your quarter pi's, and you know what all these values are on the quarter pi's. You just got to figure out which one that's coterminal with.
Okay.
Okay, and this one, basically you just plug in. T equals.
See, I thought that, but I wasn't for sure. That's what I
You
said.
better be in degree in gradient mode. That's the only other
Yeah.
thing.
Yeah, I thought about that, but I wasn't really like 100% sure on how to go about doing that, so I didn't want to do it and completely mess it up and go south.
Okay. Well, guess what? A blank is worse than a
Yeah,
wrong answer.
you're right.
Okay. Do you want to turn it in Tuesday?
Yeah, definitely can.
Okay.
All right, thank you.
All right. Thank you.
Hey, how are
Hey.
you? The quiz I did, I don't think I did it right.
Okay.
Cause like
You
you're
say
like,
you want it back?
yeah,
Did you turn it in last time?
I did it yesterday.
Yeah. Okay. Fortunately, I didn't get a chance to grade those. I don't think. Let me see.
or something?
No. Okay. If it says factor, then you just factor. If it says solve, then you get x equals something.
So this, I still, yeah, I didn't, wait. So that's number 3. Oh, okay.
Yeah.
Okay. Is it just,
Yeah. It's only when it says solve. That one's a solve. And there's one more. Find all real numbers, that's the solve number. 3 and 6 are the only two that are solved.
okay, well, I think I got it then. Maybe I don't need that. But I was wondering if I did that when I got home yesterday.
If it says factor, that's all you do is factor. Okay? You leave it at factor 1. If it says solve, then that finds a solution. Okay?
Thank you.
Yeah. Did better than you thought, didn't you?
Mm-hmm.
Okay, good deal.